Hello dear students. Today we are going to discuss surface chemistry. So before starting with the surface chemistry, let's go to the basics of surface chemistry. What are the basic terms that we are going to use in surface chemistry? So name of the chapter is surface chemistry. Now to begin with the surface chemistry, first of all we will define this what is the meaning of surface chemistry. So as the name suggests, the chemistry or the chemical process which is taking place only at the surface of another substance. That means there are many chemical reactions in which certain molecules of a substance sticks to the surface of another substance without going inside the bulk of substance. Those process which is taking place only at the surface are known as surface chemistry. Now in this surface chemistry, we have certain basic terms. So those are the basic terms, basic terminology that is often encountered in surface chemistry. First one is adsorption. So we have a term adsorption. So adsorption basically means the accumulation or the concentration or retention of the molecules of a substance on the surface of another substance. This process of accumulation, retention, or the concentration of the molecules of a particular substance on the surface of another substance is known as adsorption. So during adsorption, certain molecules comes to the surface. This is accumulated only on the surface, making it higher concentration on the surface rather than going inside the bulk. So those processes known as adsorption. So basically simply means accumulation, retention, or concentration of molecules at the surface only. Then we have adsorbate. So during the course of adsorption, certain molecules accumulates on the surface. Those molecules which accumulates or concentrates or retains only on the surface, those molecules retaining at the surface are known as adsorbate. This is something like solute in solution chemistry. Then we have adsorbent, DENT, adsorbent. So when molecules of adsorbate are retaining at the surface, so those molecules of the surface at which adsorbate molecules adsorb are known as adsorbent, and this is something like solute, this is something like solvent. So molecules of adsorbate adsorb on the surface of adsorbent, and the process is known as adsorption. So combining these two, we can have a look at this. Suppose this is solid adsorbate. On the surface of this adsorbent, certain molecules accumulates or retains. So these molecules which is retaining only at the surface are known as adsorbent. So these molecules are adsorbate. So molecules of adsorbate adsorb on the surface of adsorbent. These molecules are not going inside the bulk of substance, so this is what we call as adsorption. These molecules are known as adsorbate, and on the surface of which adsorption takes place, this is known as adsorbent. Then we have a term absorption. Absorption is retention of molecules only at the surface, whereas in absorption, molecules are uniformly distributed throughout the bulk of the substance. So during adsorption, molecules are present only at the surface of adsorbent, whereas in case of adsorbents, molecules are uniformly present inside the bulk. That means we have a substance. So inside the bulk of this substance, these molecules are uniformly distributed. This process is what we call as adsorption. So basically, this is the difference between absorption and adsorption. This is adsorption, this is absorption. So absorption, molecules are uniformly distributed inside the bulk. Adsorption, molecules are distributed only at the surface of adsorbent. So this is absorption, this is adsorption. Now there may be a certain process in which both absorption and adsorption are taking place simultaneously, and those processes are known as sorption. So in this sorption, we have adsorption plus absorption. Both are taking simultaneously. So any process in which adsorption and absorption are taking simultaneously, then this process is known as sorption. So molecules are found both inside as well as at the surface of the adsorbent. So we have molecules inside the bulk, this is absorption. Along with this, molecules are also found at the surface of the adsorbent. So this is sorption, in which both processes are taking simultaneously. So we have adsorption, absorption and sorption. So we have adsorption. Adsorption contains two components, adsorbate and adsorbent. Adsorbate molecules that are retaining only at the surface. Adsorbent on the surface of which adsorption is taking place. Absorption, bulk phenomenon, hence which uniformly distributed inside the bulk. Sorption, in which both absorption and adsorption is taking place simultaneously. Then we also have term like desorption. So desorption is just the reverse of adsorption. Adsorption means we have adsorbent molecules are adsorbing on the surface of adsorbent, whereas in case of desorption, the adsorbed molecules are removed from the surface of adsorbent. That means the process of removal of adsorbed molecules from the surface of adsorbent, that is known as desorption. So this is the reverse of adsorption. That means process of accumulation is known as adsorption. Process of removal of molecule of adsorbent is known as desorption. Then we have positive adsorption. So in positive adsorption, the concentration of the adsorbent molecules is more on the surface than in the bulk. So we may have a number of processes in which the concentration of adsorbed molecules, means the adsorbent molecules, is more on the surface rather than in the bulk. So those types of adsorption are known as positive adsorption. Or there may be some cases or process in which the concentration of adsorbate on the surface of adsorbent is less than the concentration of the substance in the bulk. If this is the case, then this adsorption is known as negative adsorption. So positive adsorption, concentration of adsorbate is more on the surface than in bulk. Then this process is known as positive. The reverse is known as negative adsorption. So in negative adsorption, the concentration of adsorbed molecule is less on the surface than in the bulk. So concentration is less on the surface than in the bulk. Then we have negative adsorption. So these are some of the terms that basically we use in surface chemistry, because often we'll be using these terms: adsorbate, adsorbent, adsorption, sorption, desorption. So before starting with the actual chemistry, so these are the basic terms that we have to come across. So once we come across this basic terminology that is used in surface chemistry, now let's go to the mechanism of the surface chemistry, or why some molecules sticks only at the surface, or what is the mechanism of this adsorption. So coming to the mechanism, of adsorption. So the question is, why certain molecules are adsorbed on the surface of adsorbent. So for this, we consider this. Suppose this is solid adsorbent. Now we'll consider a molecule inside the bulk of this adsorbent. This is adsorbent. Let's consider a molecule here. Now this molecule inside the bulk of this adsorbent is equally surrounded by another molecules. So we have a molecule here. On the opposite side, we also have a molecule. So the net force on this molecule is cancelled out. Similarly, we also have a molecule above this, below this. So on either side of the molecule inside this bulk, we have molecules on the opposite side. So that means the net resultant force experienced by this molecule inside the bulk is 0. So net force is 0. So the net attractive or repulsive force experienced by this molecule inside the bulk is 0. Now similarly, let's consider another molecule at the surface. So we have a molecule here. This molecule is present at the surface of adsorbent. Now this side we have a molecule, on the opposite side we also have a molecule. Below this we have a molecule, but above this there is no molecule. Similarly, look at this, on this side we have a molecule, and on this side we have a molecule, but above this there is no molecule. So when we consider a molecule present at the surface of this adsorbent, this molecule experience a net downward force. Why? Because this is actually a net downward force, because above this surface there is no molecule. So this molecule at the surface experiencing a net downward force is said to be under strain or stress or tension. That means these molecules present at the surface is always at tense state. So when the molecule is at tense state, that means this molecule is having some residual force, that is downward force. Because of this strain, any molecule having strain is having high potential energy. So given a chance, these molecules present at the surface will try to relieve its tension or stress. So these molecules present at the surface having some residual force will try to attract the gas molecules when placed above this. As a result of this, these gas molecules will try to stick on the surface. When the gas molecules strike or sticks at the surface, the residual force experienced by these molecules will be satisfied. As the residual force is satisfied, the molecule at the surface will have its tension relieved. So we simply say every molecule present at the surface due to this net downward force is always in tense state. To relieve this tension, these molecules will try to attract gas molecules above this surface. Things of strain. So this is the mechanism of adsorption. So all the molecules present at the surface will have some net downward force, that is some residual force. To relieve this residual force or to dissatisfy this residual force, these molecules present at the surface of adsorption will try to attract the gas molecules. When the molecules adsorb on the surface, the residual force is satisfied, and this is the reason why adsorption of molecules on the surface of adsorbent takes place. So this is the mechanism of adsorption. Now, once we know the mechanism of adsorption, there are certain thermodynamics that is involved in adsorption. So coming to thermodynamics of adsorption, now when we say the thermodynamics, so we'll take the help of delta S, that is heat of adsorption, or simply say enthalpy of adsorption. Now, while discussing the mechanism of adsorption, we say that molecules at the surface is having net downward force or residual force. So molecules present at the surface is having high potential energy. Now, because of this molecule will try to relieve the residual force. As a result, molecules are accumulating on the surface of this adsorbent molecule. Now, when the molecules adsorb on the surface, the residual force on this molecule is relieved or satisfied. As the residual force is satisfied, some energy is released, means the surface energy of molecules is decreased. Because this is relieving its strength, we have to release strain, means stability has to increase, means gaining the stability or satisfying the residual force. So when these molecules adsorb on the surface of this adsorbent, surface energy is released. So surface energy release means energy must be released by the molecules present at the surface. So that means enthalpy of adsorption is always negative. That means heat is always released when adsorption takes place. Negative because surface energy is decreased. If the surface energy of the molecule is decreased, means the molecule has to release energy. That means for any process of adsorption, there is decrease in enthalpy or heat is released, or simply we say that is adsorption process is always exothermic process. So adsorption is always exothermic. Why? Because these surface molecules, the energy of surface molecule is always decreased due to adsorption. That means this molecule has to release energy to the surrounding. As a result of this releasing of energy by the molecules present at the surface, the process comes out to be exothermic. Second thermodynamic parameter, that is entropy change, delta S. Entropy change during the process of adsorption of gas molecules on the surface of adsorbent. So suppose look at this, we have a gas molecule here. Now this gas molecule, before adsorption, this is having a relatively more random motion. Means its freedom is more. So when we say that there is a random motion or more freedom, we say that this molecule is having high entropy value. Now as this molecule adsorb on the surface, when the molecules adsorb on the surface, the restriction, the freedom of molecule is restricted, because molecule is bound to the surface of adsorbent by some forces. When the molecules of gas is adsorbed on the surface of adsorbent, the freedom of this gas molecule is less. As the freedom is less, the randomness in the motion of this gas molecule is decreased. That means before adsorption, these gas molecules were having high entropy. When the gas molecules adsorb, the randomness is decreased. So decrease in the randomness means entropy change during the process of adsorption will always be negative. That is more random or more freedom. When accumulates on the surface, freedom is restricted. So there is a decrease in random motion of the molecules of gas when adsorption takes place. So therefore, for any adsorption process, the entropy change is always negative. That means there is always decrease in entropy during adsorption process. So we have looked at this. Enthalpy change is negative. It is always released during adsorption. And entropy change for any adsorption process is always negative. That means there is a decrease in randomness or entropy. Now, once we look at delta H and delta S being negative, then we have another thermodynamic parameter, that is delta T, or change in free energy. Free energy change. Now for any process to be spontaneous, the parameter that we have is delta T. So delta T defines whether any process will be spontaneous or non-spontaneous. Now this adsorption of gas molecules on the surface of adsorption being spontaneous, delta G value has to be negative. So now look at this, we have delta S negative, delta S negative. Combination of these two gives another thermodynamic parameter, that is delta T, which is defined as delta H minus T delta S. So delta S is a negative, so negative T delta S, this comes out to be positive, delta H is negative, so this difference has to be negative for a process to be spontaneous. So since this process is spontaneous, adsorption being spontaneous, this delta H negative value must be greater than minus T delta S, which is a positive value. Since the difference is negative, So we say the process is spontaneous. Initially, when the surface is completely unoccupied, more gas molecules will absorb on the surface. So initial stage delta H will be more. That means the value of delta G negative value will be more at the initial stage of absorption. As more and more gas molecules absorb on the surface area decreases or the process of absorption decreases. So delta H negative value will decrease. So ultimately stage comes when the value of delta H, that is negative value, and the value of minus T delta H becomes equal. At that process, delta T becomes 0, that is equilibrium state will be achieved. So at the initial stage of absorption, delta H value will be more negative, so delta T will have more negative value. But as the process continues, less amount of heat is released. As the less amount of heat is released, the difference becomes less and less negative, and ultimately stage comes when the negative value and the positive value both are equal at that place, and absorption equilibrium is achieved. So simply say, during the course of absorption, delta G is negative. So since delta G being a negative, process is spontaneous. So why delta G is negative? This heat of absorption is greater than T delta H. Delta H being negative, so this term comes out with positive term, so negative term is greater than positive. But during the course of absorption, the negative value of delta G decreases, that means delta H value decreases. So this is the thermodynamics of absorption. So simply saying, all absorption processes exothermic. Why? Because surface energy of molecule is really decreased. Delta S entropy change is negative because before absorption molecules was having more freedom, more randomness. On absorption, freedom is restricted because molecule is bound to the surface by some forces, so freedom is decreased. So therefore, delta S is negative. Process being spontaneous, delta T, which is a combination of delta H and delta S, should be negative. The initial stage, delta G will be more negative because more gas molecule can be easily absorbed on the surface. So delta H value is more negative. As the absorption continues, delta H negative value decreases. So ultimately stage comes when delta G comes out to be 0. That means this value equals to this value. So we have adsorption equilibrium. So this is the mechanism and the thermodynamics involved in adsorption process. Once we have this mechanism and thermodynamics of adsorption process, let's define the types of adsorption that we often encounter in surface chemistry. Types of adsorption. So basically, adsorption is of two types: chemical adsorption and the physical adsorption. Now let's see what is chemical adsorption and what is physical adsorption and the basic difference between these two. So let's have a quick comparison between these two. Physical or physisorption, and another one is chemical or chemisorption. So we have two types of adsorption: physical adsorption and chemical adsorption. Physical adsorption is known as physisorption. Physi means physical, sorption for adsorption. Similarly, chemical or chemisorption. Now, Coming to definition of this physical adsorption and chemical adsorption. So, in physical adsorption, the attractive force between the molecules of adsorbate and the molecules of adsorbent is weak physical force, that is what we call as van der Waals force. So in case of physical adsorption, there is no actual chemical bond that is formed between the molecules of adsorbate and adsorbent. So the only attractive force that is operational between the molecules of adsorbate and adsorbent is weak van der Waals force. So because of this weak van der Waals force, molecules get adsorbed on the surface of adsorption. So physisorption means due to weak physical force. Due to weak physical force, which is nothing but van der Waals force. So adsorption due to weak physical van der Waals force is known as physical adsorption. So when we say a weak van der Waals force, then there is no actual chemical bond that is formed between the molecules of adsorbate and the adsorbent. Now coming to chemical adsorption or chemisorption. So as the name suggests, chemical. That means a chemical bond is formed between the adsorbed molecules and the adsorbent. That means in case of chemical adsorption, there is actual chemical bond formed between the molecules of adsorbate and the adsorbent. This type of adsorption is known as chemical adsorption due to actual chemical bond. Adsorption due to actual chemical bond between the molecules of adsorbate and adsorbent. So first, this is the definition between physical adsorption and chemical adsorption. So physical due to weak van der Waals force, chemical due to actual chemical bond. Next, now when we say look at this, there is a weak physical force between molecules of adsorbate and the adsorbent. This physical adsorption is multi-molecular layer formation. That means because any molecules can have a weak van der Waals force. Suppose this is the molecules of adsorbent. So when certain molecules comes here, there is a van der Waals force here. So this molecule will be closest to the surface. This will have the strongest van der Waals force. Behind this, we have certain other molecules. So this molecule can also have a van der Waals force. So we have one layer, then we have second layer, third layer. That means in case of physical adsorption, always there is a formation of multi-molecular layer. Whereas in case of chemical adsorption, since there is an actual chemical bond formed between the molecules of adsorbent and adsorbent, only single layer will be formed, that is unimolecular layer is always formed. So physical multimolecular layer, chemical single layer is formed. In case of physical adsorption, activation energy for this physical adsorption is very less, whereas for chemical adsorption, since actual chemical reaction is taking place between the two molecules, so activation energy is more here. So when we compare the activation energy of chemical adsorption and physical adsorption, activation energy of chemical adsorption is always more than physical adsorption. Now we have a thermodynamic parameter, that is heat of reaction. So heat of reaction for both physical as well as chemical is negative, both are exothermic. So this delta H is less negative and basically this is in the range 20 to 40 kilojoule per mole. When we compare this with delta H of chemical adsorption, this is more negative and this range is 80 to 120 kilojoule per mole. So during chemical adsorption, more amount of heat is released because of actual chemical bond formation, whereas in case of physical adsorption, only V van der Waals force is there, so less amount of heat is released. Now this physical adsorption or chemical adsorption increases with surface area of adsorbent. That means if the surface area of adsorbent is small, so more amount of gas molecules can be absorbed on the surface. So simply we say the adsorption is directly proportional to the surface area of adsorbent. Same case is in case of chemical adsorption, increases with surface area of adsorbent. So both this chemical adsorption and physical adsorption is proportional to the surface area of adsorbent. This physical adsorption decreases with increase in temperature. That means when we consider the physical adsorption, so we keep on changing temperature. As the temperature is increased, physical adsorption is decreased. Now let's see why this is so. Physical adsorption is due to weak van der Waals force. So if you keep on increasing, this van der Waals force will take. So as the temperature is increased, the desorption process will take place. As the desorption process is increasing, so adsorption process will decrease. Whereas in case of chemical adsorption, initially with increase in temperature, chemical adsorption increases and this reaches a maximum point, and beyond this maximum point, adsorption again decreases. So initially increases initially with increase of temperature, then again decreases with increase of temperature. So look at this, in case of physical adsorption, there is a continuous decrease with increase in temperature, because increase in temperature, the strength of van der Waals force decreases, so desorption process will take place. As the desorption process increases with increase in temperature, the adsorption process is decreased. Now in case of chemical adsorption, initially increase with temperature, then decreases. So let's see why initially adsorption increases with increase of temperature. Now we are having a chemical bond between these adsorbent molecules and adsorbent molecules. So chemical bond formation requires some activation energy. Now the molecules having energy greater than minimum energy, that is activation energy, only those molecules will lead to chemical bond formation between the molecules of adsorbent and adsorbent. As the activation energy is more, so on increasing temperature, more fraction of gas molecules will cross this minimum energy level, and if number of gas molecules crossing over this minimum energy barrier is increased, chemical bond formation will increase. Now after certain period, on increasing temperature, this adsorption decreases, because once after formation of this chemical bond, if you keep on heating that particular molecule, the molecule will have more kinetic energy, will have more energy. As a molecule gains more energy, the tendency for this bond breaking will increase. So initially bond formation increases because more molecules are crossing over this minimum energy barrier, that is activation energy. As the bond is formed on increasing temperature, molecule gains more energy, so tendency for bond breaking starts. So this is the reason why initially is increased and decreased with temperature. So graphically we say this is adsorption with temperature. So initially this is increases, then again decreases. Adsorption versus temperature. What is physical adsorption? Adsorption versus temperature. So there is a continuous decrease. So this is the difference between the effect of temperature on physical adsorption and chemical adsorption. This is temperature effect. This physical adsorption is non-specific. Non-specific. That means every gas molecule will show some sort of physical adsorption on every solid adsorbent, because the attractive force between the molecules of adsorbent and adsorbent is always the van der Waals force. So we can see if this type of adsorption is non-specific in nature. While look at this, in case of this chemical adsorption is always specific in nature. Specific in nature means only those molecules which have a tendency, which can form the chemical bond between the two, will have show this chemical adsorption. So this chemical adsorption is specific. Why? Because molecules of adsorbent and adsorbent has to form a chemical bond. If the molecule cannot form a bond, then there is no chemical adsorption. So this is specific in nature, this is non-specific in nature. The reason is this van der Waals force and this chemical bond. Physical adsorption is always reversible. So physical adsorption is reversible only because of this we are having a van der Waals force. So van der Waals force, there is no actual chemical bond formed between these physical two molecules. So this process is always rigid. That means adsorption and desorption both are taking simultaneously. Whereas this chemical adsorption is non-reversible. That means once chemical adsorption takes place, there is a chemical bond between two molecules of adsorbent and adsorbent. So when we try to dissolve the molecule, some other compound is formed. That means this shows the non-reversible nature of this chemical adsorption. So this is the basic difference between these two types of adsorption, that is physical adsorption and the chemical adsorption, their properties. Now after these types of adsorption, we'll go to factors affecting adsorption. So we have factors affecting adsorption process. So the first factor that affects an adsorption process is nature of adsorbate molecule. So we are discussing adsorption of gas on the solid surface. So nature of adsorbent plays a very important role in adsorption. So basically what we found is those gas molecules which can be easily liquefied has a strong tendency to for adsorption. So gas molecules which can be easily liquefied or more easily liquefiable gas show strong adsorption properties. So now coming back to gaseous state, so gas molecules with more liquefiable, only those molecules which can be more easily liquefied will have larger critical temperature. So gas which can be more easily liquefied means gases whose critical temperature is more will have strong attractive force. As the attractive force is more, adsorption will be more, because adsorption basically depends on attractive force between adsorbent molecules and adsorbent molecules. So gas molecules which can be easily liquefied will have larger critical temperature, and the one having larger critical temperature will have strong van der Waals attractive force A. So as a result, gas molecules will have a strong adsorption property. So this is nature of adsorbent. So simply saying, gas with larger critical temperature, which is directly proportional to van der Waals attractive force. So larger the critical temperature, or simply more easily liquefiable, will have larger or stronger adsorption property. So suppose we have the number of gas molecules and their critical temperatures are mentioned. So gas with larger critical temperature will have a strong tendency for disadsorption. Why? Because this gas with larger critical temperature has got strong attractive or intermolecular attractive force. So adsorption is proportional to attractive force. So rate of adsorption of those gas molecules which have larger value of critical temperature or more easily liquefiable will have stronger adsorption property. Second is surface area of adsorbent. So rate of adsorption is directly proportional to the surface area of the adsorbent. So this is directly proportional to surface area of adsorbent. So as the surface area is more molecules can adsorb on the surface of adsorbent. As the surface area is less number of gas molecules will adsorb on the surface of adsorbent. So this rate of adsorption is directly proportional to the surface area of adsorbent. Now basically this is the reason why we use catalyst in powder form, because heterogeneous catalyst is basically based on the adsorption theory. So when we use heterogeneous catalyst, we always use this catalyst in powder form. So when we make the powder form, finally powder form, the surface area is increased. If the surface area is increased, the rate of adsorption is increased. As the rate of adsorption is increased, the rate of reaction also increased. So this is the reason why we use adsorbent in powder form. So the reason is adsorption is directly proportional to the surface area of adsorbent. Third factor that affects the rate of adsorption is the most important, that is effect of temperature. So in case of physical adsorption and chemical adsorption, we have just discussed now. Physical adsorption is inversely related to temperature. As the temperature is increases, the rate of physical adsorption decreases. Physical adsorption is inversely related to temperature. We have discussed the graph, that is the rate of adsorption, this is temperature. So we have explained this also. Physical adsorption, basically there is weak van der Waals force. As the temperature is increased, van der Waals force decreases. As the van der Waals force decreases, desorption is increasing, so adsorption process is decreasing. In case of chemical adsorption, initially rate of adsorption increases with increase of temperature, then again decreases. Again we have explained this based on reaction parameters. This is adsorption and this is temperature. So in case of chemical adsorption, actual chemical bond is formed between the molecules of adsorbent and adsorbent. So chemical bond formation requires some activation energy. So only those molecules crossing this minimum energy barrier will undergo chemical bond. So initially on increasing temperature, the fraction of molecules crossing over this energy barrier is increased. As the fraction of molecules is increased, that of adsorption also increased. Once the chemical bond formation starts, after this chemical bond formation or adsorption process, if you keep on increasing temperature, the molecules adsorbed on the surface of adsorbent will gain more energy. As the molecule gains more energy, the molecules will have more vibration, stretching, etc. etc. And when we increase the temperature, tendency for breaking of this bond increases. As the tendency for breaking of bond increases, or means simply we say desorption increases. As the desorption increases, adsorption will decrease. So this is the variation of chemical adsorption with temperature. So initially increase, reaches a maximum point, then decrease. So this is adsorption process is more than desorption. Beyond this point, desorption process is more than adsorption process. So continuously this decreases. After this, we have effect of pressure. Effect of pressure on the rate of adsorption. Now this effect of pressure on the rate of adsorption is defined by two equations. So first one is Freund-Leach isotherm. Isotherm. Why we use the term isotherm? This is at constant temperature. So variation of the rate of adsorption with pressure at constant temperature is known as isotherm. So isotherm explains the rate of adsorption with pressure at given temperature. So this is Freund-Leach isotherm. This was the name of scientists who proposed this isotherm. So Freund-Leach isotherm, basically this is used for explanation of physical adsorption, because physical adsorption, that is formation of multi-molecular layer adsorption process, can be easily explained by this Freund-Leach isotherm. So Freund-Leach basically used for explanation of physical adsorption. Now this Freund-Leach isotherm is based on this equation: x by m is equals to k p raised to the power 1 by n. So let this be equation A. Let's expand the terms involved here. This x is mass of gas adsorbed. So extent of adsorption is nothing but mass of gas adsorbed per gram of adsorbent, that is defined as extent of adsorption. K is a constant. P stands for pressure, and this N is another Freund-Leach parameter or Freund-Leach constant whose value is greater than 1. So we have the equation. So x by m, that is extent of adsorption, is directly proportional to pressure raised to the power some power, that is 1 by n, where n is a constant whose value is greater than 1. Now equation says extent of adsorption is directly proportional to pressure. That means if we increase pressure, amount of gas adsorbed or extent of adsorption will increase. graphically this is extent of adsorption, this is pressure. So look at this, suppose this is temperature T1, this is temperature T2, this is temperature T2. So at this temperature T1, X bar is less, T2, X bar is slightly more than this T1, X bar is more than. So moving from temperature T1 to T2, temperature decreases. At high temperature, adsorption is less, low temperature, adsorption is more. So T1 is greater than T2, greater than T3. So for the same gas that is adsorbed on a given surface of adsorbent at a given pressure, on increasing temperature, rate of adsorption decreases, or on decreasing temperature, extent of adsorption increases. Now look at this. This extent of adsorption, initial stage increases, then it increases slow, and after this becomes fixed, constant. So that means equation says X by M, extent of adsorption, is proportional to pressure. As the pressure increases, X by M has to increase. But after certain period, it reaches a saturation point. Now we have to explain why this reaches saturation point. That means this extent of adsorption does not increase beyond certain point. So first thing is clear. If this extent of adsorption increases as the temperature increases at a given pressure on the same solvent adsorbent surface, after certain point this becomes a saturation point. So simply saying, look at this. Adsorption initial stage is increase is slow, then after this point this is fixed. There is no more increase in adsorption as the pressure is increased. So first let me explain why this adsorption remains constant after a certain pressure. So at this point, if we keep on increasing pressure, there is no more increase in extent of adsorption. So the reason being, initial stage, suppose this is a surface of adsorbent. At initial stage, the surface is completely unoccupied. So initial stage, when the surface of adsorbent is completely unoccupied, more gas molecules can be easily adsorbed. So at the initial stage, if you increase the pressure, there is very large increase in the adsorption. Now after certain gas molecules adsorb on the surface of this adsorbent, the surface area of this adsorbent is decreased. As the surface area of this adsorbent decreases, the rate of adsorption decreases. After certain period, when all the surface of this adsorbent is completely occupied by gas molecules, there is no space left for gas molecules to adsorb. Though we are increasing pressure, but there is no surface area left for gas molecules to adsorb. So on increasing pressure beyond this point, no more space is left, so no more gas adsorption. That means at this particular point, a saturation is reached, and this point is known as saturation adsorption pressure to saturation point. So saturation point is reached means the whole surface area of adsorbent is completely occupied by gas molecules. So there is no more space left for another gas molecules to adsorb. So since there is no surface left for gas molecules to adsorb, Beyond this saturation point, though we are increasing pressure continuously, then also the rate of adsorption or extent of adsorption remains constant. So physically we can explain the initial surface area is large, so gas molecules can easily adsorb, so rate of adsorption is very high. As the surface area decreases, adsorption is decreased. As the surface area is no surface area is left, so extent of adsorption remains constant. So this is the variation of extent of adsorption with pressure P. So one thing is beyond this saturation point, no more adsorption because surface area is completely occupied by gas molecules. Now we have to see the validity of this graph. Taking logarithm of this graph, we have log x by m is equals to logarithm of k plus 1 by n logarithm of pressure. So if you look at this logarithmic form of this previous isotherm, we have equation of straight line. Let this be y. This is constant c. This 1 by n is slope and log p is x. So we have equation of straight line y is equals to mx plus c. So the validity of these previous isotherm will be checked by use of this equation. If this log x by m versus log p graphs comes out to be a straight line, then the previous isotherm is okay. But if this does not give you a straight line, then validity of previous isotherm is not possible. So graphically, we can say we have log x by m and logarithm of p. So when this log p is 0, log x by m is equals to log k, so we have this. Slope is positive, that is 1 by n. So extrapolation to 0 value, this gives you log k. So from the graph, that if y-intercept, that is intercept along this x by m coordinate, gives you the value of log k. So we can easily define the value of k. That is the constant used in this previous isotherm. Now, for this graph, the slope, let this be the theta, then slope is equal to tan theta. So this tan theta is equal to 1 by n. So once we know the slope of the graph, then we can easily define this n also. So from this graph, if the graph happens to be a straight line, then we can define the value of log k. Once we define the value of log k, then the constant k is defined. And from the graph, we can find the value of slope, and from the slope, we can define the value of n. And in this, the value of 1 by n changes from 0 to 1. So this is how we define the value of k and n, which is the constant involved in previous isotherm. So first thing is validity to be checked by this logarithm equation, and from this logarithm equation we can define this value of k and n. Slope is 1 by n, x by n, sorry, intercept along log x by n coordinate is log k. Now observation from this previous isotherm. At low pressure, at low pressure, when the pressure is low, at low pressure this 1 by n is equals to 1. When the value of 1 by n is equals to 1, so from this equation 1 we have x by m is equals to k P raised to the power 1. So at low pressure condition, the value of 1 by n being 1, Freundlich isotherm says extent of adsorption is directly proportional to pressure raised to the power 1. That means this is the first order kinetics. So at low pressure, the extent of adsorption follows first order kinetics. So if at low pressure zone, on increasing pressure, this x by m increases continuously in a straight line way. So order is first order kinetics directly proportional to the pressure. A high pressure. When the pressure is high, this 1 by n is 0. So if 1 by n is 0, then from this equation 1, we have this x by m is equal to k pressure raised to the power 0. So something raised to the power 0 is 1. So we say this is constant. So in high pressure, though we are increasing pressure, the extent of adsorption remains constant. That means at this point, no more surface area is left for adsorption, so the saturation point has reached. Beyond the saturation point, increasing pressure does not have any effect on this extent of adsorption, so the graph is constant. And in some intermediate pressure, 1 by m is between 0 and 1, so we have this equation, x by m is kp1 by n. So this is the observation. So at low pressure, extent of adsorption follows first order kinetics. At high pressure, this is following zero order kinetics. So this is the effect of pressure on Freundlich isotherm. This is used to explain physical adsorption. So considering this effect of pressure at low pressure, high pressure and intermediate, which follows this event kinetics. So the graph that we observe, that is extent of adsorption versus pressure. So at low pressure, extent of adsorption is first order kinetics. So we have equation of straight line passing through origin. So we have this. That is straight line increase. So rate of adsorption increases steeply because of this first order kinetics. After this, look at this. At intermediate pressure, this is not following first order kinetics or zero order. So rate of adsorption is decreased. So there is a tapering in the graph. So this is intermediate zone. Now at high pressure zone, extent of adsorption is constant following zero order kinetics. So again, the rate of adsorption is constant. So these point, that is what you call as saturation point or PS, saturation pressure. So this is high pressure zone. At this high pressure zone, we have this x by m is equals to k, that is zero order. This portion of the graph, that is low pressure zone. At this low pressure zone, we have x by m is equals to k into p, that is first order kinetics. So that is steep increase in extent of adsorption. This portion, intermediate pressure. At this intermediate pressure, equation is H by M is equal to P raised to the power 1 by N. So this is the explanation of the graph observed. So low pressure, H1 is Kp, first order, so there is a line phase. High pressure, H1 is Kp, or simply say K, P naught is 1. So zero order kinetics, so extent of adsorption remains constant. The intermediate portion, extent of adsorption is decreased. At this point, saturation point is achieved. So this is French isotherm. So this French isotherm does not follow above this certain pressure region. So this is applicable beyond this region only. So this equation basically explains physical adsorption. Now there is one more equation which can be used for explanation of chemical adsorption. That is Langmuir isotherm. First of all, this is the name of scientist who gives propose this isotherm. This Langmuir isotherm is basically based on kinetic theory of gas molecules. So Langmuir isotherm, Langmuir take the help of kinetic theory of gas to explain this isotherm. Langmuir isotherm is basically based on certain assumption. Assumption is all the molecules, all the sides on the surface of gas adsorbent are equivalent. That means all adsorbing sides are equivalent. And when we say all adsorbing sides are equivalent, the molecules adsorb on the surface of adsorbent. So the molecules adsorbing on other surface doesn't have any effect on the next molecule. So Langmuir says that all adsorbing sides are equivalent and the molecules adsorb on a particular side is independent of the molecules adsorbing on another side. Second says this Langmuir isotherm says only monomolecular layer is formed. That means actually there is a chemical bond formed between these adsorbent molecules and adsorbent molecule. So Langmuir isotherm monolayer formation, that is chemistry-1. Next he says during adsorption an irreversible process like adsorption and desorption both are taking place simultaneously. Initially gas molecules comes on the surface, then the molecules get adsorbed, and after this molecules again leave the system, that is adsorbed molecules again leave the system, that is desorption. So adsorption and desorption both are taking place simultaneously. So these are the basic points considered by Langmuir isotherm. So first thing is this is basically used for chemistry-1. There is a monolayer formation because there is a chemical bond formed between the molecules of adsorbent and adsorbent. Second, this is based on kinetic theory of gas. Third, both adsorption and desorption takes place simultaneously. That means first molecules adsorb, then adsorbed molecules again leave the surface of adsorbent. Third, all adsorbing sides are equivalent and adsorption of one molecule is independent of the molecules adsorbed on adjacent side. So these are basically points of Langmuir isotherm. Considering this Langmuir proposal equation, says H by M is equal to AP divided by 1 plus BP, where P stands the pressure, H is the mass of gas adsorbed, M is the mass of adsorbent on whose surface gas molecules are adsorbed. A and B are Langmuir constants. So we have to explain this. This is equation, main equation. P is the pressure, A is the Langmuir constant, X by M is the extent of adsorption. At very low, at very low pressure, when the pressure is very low, so the term dP will be very small. So 1 is much greater than dP. So therefore 1 plus dP is approximately equals to 1. So at very low pressure, so from equation 1 we have, look at this, H by M is equal to P. So at low pressure, product of P and P is very small. So 1 plus ABP is approximately 1. So therefore X by M is equal to AP. So look at this, X by M is directly proportional to P. And this is first order kinetics. So low pressure follows first order kinetics. So simply this is again something similar to that of French isotherms. At high pressure, if the pressure is high, this product dP is much greater than 1. So therefore 1 plus dP is approximately equal to dP. So therefore from this equation, X by M is equal to AP by dP, or we say A by B. So A is the constant, B is the constant, so we say this is constant. So at high pressure, this X by M is independent of pressure and it is zero order. At some intermediate pressure, look at this, we have a pressure in numerator as well as pressure in denominator. So there is a compromise within these two, so the rate of adsorption is slightly less. Now, to find the value of this A and B, we'll just modify this equation how to find the value of A and B. So we have looked at this equation 1. Take the inverse of this equation 1. We have M by X is equals to 1 plus BP divided by AP is taking inverse of equation 1. Inverse of equation 1. So this is, M by X is equals to B by A plus 1 by AP. Now we have this M by X is equals to B by A plus 1 by AP. So this is something like equation of straight line. So we can assume this to be Y, B by A is the C, 1 by A is slope, and 1 by P, this is X. So we have equation of straight line. So we have a graph. So we have M by X versus 1 by P graph. So X by M versus 1 by P, equation of straight line with slope positive. So if 1 by P is 0, M by X is equals to B by A. So extrapolation at 0 value, this gives you intercept. This intercept is equals to B by A. And the slope of this graph, we have this tan theta. So slope is equals to tan theta. So this is equals to 1 by A. So from the slope, we get the value of 1 by A. From this, we will get the value of A. Once we know the value of A, we can define this B by A, that is from this intercept. So this graph, by use of this graph, we can find the value of B and A, that is the constant involved in Langmuir isotherm. So this Langmuir isotherm is more appropriate for explanation of chemical adsorption. So this is the two isotherms that basically we use for explanation of extent of adsorption of gas on the surface of adsorbent molecules, both for physical as well as chemical adsorption. Now there are certain cases of adsorption of solute from solution phase. So adsorption in solution phase adsorption in solution phase. So for this adsorption of solute from solution, both Fred-Lewis and Langmuir is applicable. So both Fred-Lewis and Langmuir isotherm is applicable for adsorption of solute from solution phase. So the only difference is the pressure term should be replaced by the concentration term. So from Fred-Lewis isotherm, we look at this x by m, that is the extent of adsorption is equals to Kc raised to the power n, where C is the concentration, and the rest as usual x by n, 1 by n. The value of 1 by n is from 0 to 1, and the value of n is greater than 1. You can get the help of logarithm equation also. Everything remains as it is. For this Langmuir isotherm, x by m is equals to AC divided by 1 plus BC. So again, look at this, A and B, these are level constants, C is a concentration. So all the facts that we have explained for Fred-Lewis isotherm and Langmuir isotherm, both are applicable for adsorption of solute from solution. So this is the effect of pressure on adsorption and effect of concentration on adsorption from solution. So during this, look at this adsorption, there is found to be proportional to the concentration of solute that gets adsorbed on the surface of adsorbent. So this is Fred-Lewis isotherm and Langmuir isotherm. So basically, what is the difference between these two, and how different parameters are explained, and how the graph can be explained, and low temperature, low pressure condition, high pressure condition, intermediate pressure condition, and how to find the values of various constants. So this is the factors affecting the rate of adsorption and basically isotherm, that is effect of pressure at constant temperature.